presentation earlier, the scientists like lots of data, but a lot of times they can't get it to the ground. Of course, we've got ground systems and transceiver vendors trying to come up with ways to get more data to the ground, and X-band and Ka-band and so forth. But at the same time, for this community, we need to be thinking about how to utilize architectures like that and how to do more on board with limited resources and so forth. So hopefully you'll be thinking about that. Coming up next, we have Jonathan Wilmot to talk about the state of electronic data sheets and autocoding software using CCSDS data sheets. So, Jonathan.
Okay. So this builds on from some of the talks this morning for folks that were around for that with the CCDD tool and the Simulink interface layer. So anyway, this is more about there's an upcoming CCSDS electronic data sheet standard that we've been working on for the past couple of years. So yeah, I'm Jonathan Wilmot from Goddard, working the flight software branch. I think that's the right one. So we have an agenda, so we're going to go through these. So what is an electronic data sheet? So it's a formal specification of a device, software interface, in a machine-readable format. It's unambiguous and machine verifiable. We picked XML. There's many other things we could have picked, but we picked one. You can code from this to many other different interface or different languages. So it's delivered with a device, a subsystem, or a software component. So they go together. It's not an ICD. It doesn't specify how you're going to use that particular component in a system. It has things like constraints, like this application will accept commands from 10 hertz to 100 hertz, and the ICD says, well, 50 hertz. We picked that one. So I'm trying to go through some of the differences with what an ICD is. So an EDS specifies a black box view. It's not trying to talk about the insides of how the box works. It's just what does the interface look like? Is it a space wire thing with packets of this type? What are the exchange rates? It also supports state machines. So key difference, because this has come up before, what's the difference between an EDS and XTCE is that an EDS is targeted towards individual components and software items, and it also contains state machine interaction patterns, which XTCE does not. XTCE is written for ground systems. It has additional parameters and language to allow you to specify formatting information, which EDS also has, but also how the ground, like mnemonics of something. The onboard systems don't care about mnemonics. They care about the names and what the data values are. They don't care about that you called this thing some specific name. So these are some of the differences. EDS has the interaction patterns and network stack information, which XTC does not have. So there's an organization called the Consultative Committee for Space Data Systems, CCSDS. It's an international standards organization, for those that don't know. If you get a spacecraft ID, it comes from this organization, which manages the Spacecraft Assigned Numbers Authority. If you use space packets, so if you're using CFS, you're using space packets. That's also a standard that's part of this. If you're using link definitions or AOS, there's many, many different standards that are available. The one we're talking about here is coming from the Spacecraft Onboard Interface Services area, which I'm the director of, and it's the let me back up a little bit. So the EDS is defined by that organization, and it's really two different things. It's a dictionary of terms that we use with the data sheet, and it's also the XML schema itself. So we have names that are available in the baseline, but there also be other types of names that will go in there for attitude control. This common language to use in your data sheet, so you have a standard definition of what a quaternion is and these kind of things, which are very important when you're trying to make interoperable data sheets. So within that organization, we have several books. We have a green book, which is the overview and rationale for why we created this standard. We have the XML specification itself. Then we have this dictionary of terms, and the and the schema and the dictionary terms are in this space assigned numbers authority Santa registry, and they're available at that URL. So the intent here is that we provide a standard to exchange system, device, software interface definitions between organizations and agencies. So, which is why it's within CCSDS, which is an international standards organization. So that ESA or ESA folks or JAXA folks can provide the data sheet and exchange that with NASA. We know what their interfaces look like in a machine-readable format, and we can actually auto-generate many of the artifacts, which is what really the rest of this talk is about. So the vision here, long-term, some of what we have now, is that when you go buy a star tracker, it comes with a data sheet. When you go buy a thruster, it comes with a data sheet on sun sensors and so forth. And then software components. So for CFS component, there's a data sheet associated with it in CM. So when you pull that component off the shelf, you get the data sheet with it. And then you can run it through software tools and auto-generate the XTCE for the ground, auto-generate interface definitions for actual spacecraft, and do that for each of these items here, as well as the software components. So the long-term goal is actually have manufacturers provide these data sheets. And some of them already do that, but they're not standard data sheets. They're their own proprietary, usually they're XML, but they're their own schema. So we want to go through and actually have a standard that the existing manufacturers can use. And from what we've heard as feedback, they're agreeable to something like this because they're already doing it this way. And it actually opens up markets for them because it's easier for them to sell their product if it comes with a data sheet. And you know, it's easier to integrate their product and all these kind of side effects, which are very valuable. So some of the products you can get from data sheets, and you heard some of that this morning. So you can, from a software data sheet, you can use tools like the CCSDS tool to generate flight software interfaces or models of those interfaces. You can use those data sheets to create simulations of those interfaces and test procedures. You know, the XTCE or whatever ground database language you happen to be using, page displays, operational procedures, and the same for devices. You can generate all these artifacts. You can start from a model and work your way down and actually feed back up into models. Each of these paths has been prototyped or has some operational code associated with it. You know, the CCSDS is operational code. The restore mission has actually done the page displays, and everybody seems to have done this. ESA has done test procedures, operational procedures, and simulations as part of interoperability tests. So this is quite a powerful set of artifacts you need for mission development that ease integration and make more reliable software and systems. So for devices, the primary use cases are, it contains a device is delivered with a SEDS. It contains the device-specific information about what version is it, what's its serial number, and each device tends to have its own set of calibrations. So when you get that Star Tracker 1, it looks like this. Same interfaces, but now the calibration is slightly off. And so you'd pull that out of your data sheet. Data sheets also have placeholders for deployment configuration. So if in your device you have a MAC address or a 1553 address, it has a placeholder as part of the schema to be able to push that number in there. If you have some sort of tool like the CCSDS that could populate that as part of system configuration integration. A lot of them have programmable values. before you connect that device. Let me rephrase that, like test set programmable values before you bring that device in for system integration. So the language has placeholders for those kind of things. Those kind of data sheets won't validate with the generic tools out there like XML Spy, but once you've populated those fields, then it will fully validate with the existing open source tools. Well, of course, that's not quite open source, but there are versions out there that are. From that SEDS, you can autocode those interface tests. So as part of interoperability tests, we received the star tracker. It came with a data sheet. We used that data sheet to actually validate that the star tracker was as delivered by running a data stream through it. So that's very powerful. So when you get a delivery of a piece of hardware, you can know that it actually works the way they said it works before you bring it into your system and then find out it has issues or bugs. So it's very powerful to be able to do that early on. You can do that, they deliver it, they can do it prior to shipping, and then when you receive it, you can actually redo the test to make sure everything is as they've stated without going through a paper ICD and finding out after you've tested everything it's not quite right. You can use this as input into systems integration tools. We've seen heard some examples of that this morning. You can autocode tests or test set specific tests to verify that the device is compliant. So I stated that. ESA has gone through and actually autocoded device drivers from these data sheets and device models from data sheets, so you can plug them into your simulation environment. Again, they're black box device models. So you send a command, or you send a command to get some sort of response back, and the associated state machines with that. Use cases for software components are very similar, and this was one of the primary interests of, as a CFS architect, I had a big interest in this for CFS components and software architectures. And they are integrated partially in the 6.6 release of CFS and be fully integrated in the 6.7 release of CFE, sorry. So the SEDS are configuration managed with the components. So in your Git, they're put out there with it. So when you pull the two, you get a match set. If you change any interface definition, you should change the SEDS. It goes back and forth where you start with a header file for what your packets look like, or you start with a SEDS and then auto-generate the header file. You can go either way. There are tools to do that. But in any case, you want to manage the data sheet with the device, the component. Use them as inputs to your system integration tools. We have a version of tools that populate things like the application ID, which is known at system time, but not by the actual software component. It can't know what its message IDs are going to be until you actually instantiate it within a system. So we have tools to do that as part of the CFE release. We can use it, again, just like devices, to autocode integration tests, and I have some further examples of that. And then you can use, Flight Projects can use it to test individual software components or a subsystem that came from another supplier. If you have a data sheet, just like with the hardware, if you have a data sheet, you can actually test that, see that they met the interface definitions that they said they had. And then you can autocode components into different modeling languages based on the data sheet. So I have some examples, some of the things that are in data sheets now. This is there was a tool that just took a data sheet and created these state machine diagrams. They're relatively simple diagrams, again, because they're just looking at it from an interface perspective. This is I'm in the idle state, and somebody sends me a command. I get a command to get the mode. I wait for it to complete, and go back to idle. This was all in the XML data sheet that we use for the interoperability tests between ESA and NASA. Just as some background on that, anytime there's a new CCSDS standard, they have to do an interoperability test between two or more agencies or organizations. So we've just completed that, and this is just an example of some of the state machines that we used. So these are simple ones. You probably can't read this, but you can get pretty complicated in XML. This is just done for the interfaces. That's why again, it's a black box view, which is hopefully is less complicated than trying to model the whole internals of some device or software, which is not the problem we're trying to solve here. And you use other languages to do things like that, the UML if you really wanted to get fancier. This is, again, a simpler view, just a black box view of a device at the interface level. But you can do state machines and activity diagrams, and tools can put out, either diagram or a table format. Excuse me. This is something we did for a balloon mission called GAPS, which ended up being canceled for reasons outside of this. But this workflow was established for that, just as an example of the kinds of things you can do. So project-specific configuration, CCDT tool or something like that can generate that. You generate or publish out your EDSs with this processor, then you can create the databases, either a full database or a runtime database, and the header files, these products. Then feed into a compiler, and you can generate the source code or the binaries from that. One thing we did, we used Lua, and we were able to take the data sheets and actually generate tests that we could actually do in situ on the processor to test all the command paths, all the command interaction patterns, all the telemetry interaction patterns. Essentially, we auto-coding much of the software and all the tests, and then generating all the artifacts from that, which is pretty powerful. This is a notional integration. We're still working on some aspect of this. The CCDD tool can actually input and export data sheets. CFS in 6.6 has a way of taking these data sheets and generating, tables from that or code from that, and then creating header files and tables and such. Some of this work was actually it's in parallel with stuff that JSC is doing, because we have our own version of some of these things. I guess the point is here, these are things that you can create. Everybody is solving these same kind of problems, and the EDS is an important part of that whole puzzle and becomes the exchange mechanism between organizations. If you say this was proprietary, you don't have access to it, but this demonstrates the kinds of things you can do with it. Parts of these will be open source with CFS releases. This part actually is as well. Steve Lantine is working this aspect of it, which is still in work, is being done for the Lunar Catalyst program. And the idea, again, would be to take these data sheets and import and export them from the Simulink environment. So this is just, if you were here this morning, you heard about this, but from my perspective, nice thing is it can import data sheets and export data sheets. Again, the use case for this in tools like this is if you get a star tracker, you don't have to go read a piece of paper to figure out how to populate your command and data dictionary tool. You just read that in, and then the tool does all the system configuration of that. And it may spit out a new data sheet with what you've constrained it to, what are the actual data rates you're using and those kinds of things. But that's where it fits into the big picture here. It's a piece of the integration puzzle. So another use case is a very large, program, the Lunar Orbital Platform Gateway. So this doesn't have a lot of detail, but you You may have vendors providing pieces from here, like some device or thermal control system that you want to share with some other element over here, and you would provide that in the international standard, the data EDS, and then they bring it into whatever their particular tool is. Example, if this was being provided by ESA, they could be using their packet utilization standard software architecture over there, and you'd still be able to communicate with that from a CFS-based component. We've already demonstrated that. You can take commands in one format, use the data sheet to change what the payload looks like, send it across a messaging system and get it over to their system. And then they can interpret it properly. And so that can work both ways. So as an international exchange standard, it works quite well in that environment. So, because you will not be able to dictate the software architectures that each of these subsystems use, but you still want to be able to exchange messages. They all seem to use messages, so having a standard way to define that format and what their exchange patterns are with the associated timing and state is pretty powerful. So for this program, the CCSDS EDS is part of the requirements. It's included in their standard. So again, I guess I just said most of that. But so we have international partners using different software. You know, it's a fairly large program. It's a space station at the moon. They may be providing devices to other partners or subsystems to other partners, and the data sheet provides a way of integrating that more easily. Since unlike XTCE, the CEDS defines the interaction patterns of those interfaces. So as we said, we can take a ECSS, which is a European standard, and interface to our software bus over SBN and use a data sheet to describe that and autocode the outputs. A CEDS includes things like the full subnetwork stack. So this is a space packet. It's using UDP. Things like what port number it's using are included in the data sheet. It's an IP, and it's going over Ethernet. The data sheet actually defines the entire stack all the way down. So when they hand it out to somebody else, they know, hey, I need to use Ethernet, and I need to use IP, and I need to do that, and I need to do that, and here's what the format of that packet looks like. Again, this is why it's different than XTCE. From those data sheets, each partner of your international partners can put it into their architecturally specific tool chains, you know, their proprietary tools, and have something that works. When you come to integrate it, you've got this electronic definition that solves a lot of your integration problems, done correctly. And again, since it's a CCSDS standard, it is a standard that our international partners can use. There's nothing proprietary about it. Summary and status. So the hope is that our devices and software are developed and delivered with CEDS. We use these CEDS as inputs to these different tools to generate all these different artifacts. It's an international standard. So towards the end of this week, I'm sending it out to the management of CCSDS to do their final review prior to publication. So it's gone through all the interoperability tests, all the agency reviews, all the comments have been incorporated. So January timeframe, it should be done and stamped as a blue book within CCSDS. As I said, it's included in the LOPG requirements. ESA's and Mark is actually managing one of those. They have a large development process to see how they can bring it into ESA for their vendors. And they're doing one thing, which is a natural sort of extension, is they're bringing in thermal and power types of things. Like this box is 28 volts, it uses so many watts, has these other characteristics. Those kind of things are being brought in as well. That's not part of the existing standard, but it's something that's coming because it has a lot of value when you buy a star tracker. Well, how much power does it use? And having that in an electronic form rather than a piece of paper that's more prone to error. It's actively being integrated into time-space partitioning architecture on time-triggered networks. And again, as I said, we want to expand it to cover the thermal and power attributes. Things like mechanical attributes, that may be very simple because there's lots of CAD systems and already definitions, so we don't need to go into that area. It's a bunch of acronyms and other backups. So are there any questions? Sure. Are you allowed to ask questions?
Do you have an example of a device that uses EDS? Like, is there like a reference device out there? Where
we have several. Some of them were delivered from manufacturers. So Jena is a star tracker manufacturer, and I use that as an example. And we have several. We tried to actually do a Claggett reaction wheel a couple years back. And they were all definable within it, so that wasn't a problem. One of the problems we do have is a lot of these ICDs are proprietary. You have to buy it, and then they'll tell you how it works.
And then you can make the EDS for it.
And then you get the EDS. So we have some of them, but they're only used for internal study, and we can't publish them. But we have a Git server that we have a lot of these things out there.
Okay, so if you had a device like a reaction wheel that talked over an I2C bus, would you be able to? Would the EDS include like I2C commands to talk to that device, or?
So yeah, so it doesn't, like SpaceWire, I'll use that example. It doesn't say how SpaceWire works or how 1553 works. It says, but it does use language of like 1553. This thing, whatever the data units are, come over through these subaddresses. So you have to use the specific language of that subnetwork. So I2C has some specific terms. Those wouldn't be defined in the dictionary of terms, so that they probably reference the I2C standard is the way that would work. We don't have an example of that, but that would be the expectation when a device comes around that's I2C.
Okay. Yeah, I'm curious to see how we could try to integrate this for device support for CFS. I mean, I can see you already have the command and telemetry part covered.
Right, and the example I had from ESA was they actually took a data sheet and they created the device driver for 1553 device from it. You know, it's as part of their tool change, which is pretty powerful.
Yeah.
Okay, we're due for a break. I know we only got one question. If you have some other questions, I'm sure Jonathan would be happy to stay up here during the break unless he's going badly.
I'm good.
If you have some more questions for Jonathan, and then we'll reconvene in about 10 minutes. Thank you.